Okay, we're continuing on with chapter 12 on solids, and we're going to start off talking about elasticity. Let me dismiss this. I may come back when I start using my hands to talk. An object is subjected to external forces and may undergo changes in shape or size. As a matter of fact, I think there's lots of different forces that you can do. You can do a compression force where you push down on an object. You can have a sliding force. You know, if you think of your textbook, and if you have it on a table and you push, it's going to deform it, kind of make it a rhombus. Everything's going to tilt over. It has a tensile force. I mean, if you pull something, you're putting tension on it and stretching it. Then there's different factors. We're not going to study these, but I'm just telling you, there's a Young's modulus, there's a bulk modulus, there's a shear modulus, there's a thing called a Poisson ratio, where if you can imagine an eraser, where you push an eraser and it's going to bulge. I mean, if you were to take a cube of copper or something like that, and you push on it, it's not going to bulge. But you take an eraser, you push on it, it's going to bulge. There's all these kind of factors that describe how different materials react under different forces. An object subjected to external forces may undergo changes in shape and or size. A body's elasticity is a measure of how much its size changes when a deforming force is exerted on it, and how well it returns to its original shape. Now, we think of something like Play-Doh as being very elastic. You can squash it and form it, make it into like a string, but it's not really very elastic. But based on that definition, because how well it returns to its original shape, well, Play-Doh is not going to return to its original shape on its own. So it is not elastic. That's the common use of the term. Materials that require more force to stretch are more elastic, contrary to common usage of the term. Materials that do not return to the original shape are called inelastic. So Play-Doh would be inelastic. A metal spring would be considered elastic, or a metal bar, unless any of these things that you stretch them or bend them beyond their elastic limit, they will no longer hold their shape. Which is more elastic, steel or rubber? Well, are they equally elastic? Which one's going to return to its form? It takes more force to do steel, so it's actually the steel that is more elastic. It takes more force to stretch a steel wire than to stretch a rubber band. Also, the steel regains its original shape much quicker than rubber after the force is removed. Okay, now Hooke's law. The extension of a spring is directly proportional to the force applied to it. The force is proportional to the extension. And as a matter of fact, the force, there's actually, we'll get to this later, but Hooke's law is force is equal to minus kx. And if you think about it, if you have a spring and you pull it, which way is the spring pulling? It's pulling back up. So you stretch it X number of, let's say, centimeters. Well, the force is up. And the same, if you compress a spring, if you were to compress a spring, its force is in the opposite direction. So that we'll learn later that the force, not only is it proportional to the change in X, it's actually a negative kx is the Hooke's law. So, if you put a little bit of weight, you're going to stretch this spring a little bit. A little more weight, you stretch it more, and so on. Well, let me dismiss that. A 10-centimeter long spring extends to 12 centimeters when a 1 kilogram load is suspended from it. What would be its length if a 3 kilogram load were suspended from it? Well, it starts off at 10 centimeters. So if you put 1 kilogram, it's extended 2 centimeters from its original shape. So we're going to assume a 2 centimeter length for each kilogram. So if you add 3 kilograms, it's going to be 16. So if it's 2 for 1 kilogram, it'll be 6 for 3 kilograms. So the answer would be 16. Oops. And there it is. Since extension is linearly proportional to the stretching force, tripling the suspended mass triples the extension from 2 centimeters to 6 centimeters, including the unstretched length. The ultimate length is 10 centimeters plus 6 centimeters, which is equal to 16 centimeters. Okay. Tension and compression. When look at this beam, we're going to assume it's either, you could call it a wood beam or you could call it a steel beam. When something is pulled, it is in tension. Squashed is in compression. So when a girder distorts, as shown, it is under tension on the upper side and under compression on the lower side. You can see that this portion, the top portion, is elongating, and this one is kind of being forced together. It's compression. So those are the difference between tension and compression. When a girder distorts is shown, it is under tension on the lower side, in which it's pulling apart on the lower side, and it's on compression on the upper side. Okay, often construction uses an I-beam, which is it's called an I because the cross section looks like the letter I. You can see the letter I. When used as shown, the shape of the I-beam maximizes strength because the top under tension and the bottom under compression had the most material. And there's the most material here for compression, and a lot of material here for the tension. It minimizes the weight because the middle of the beam that is not under stress has the least material. So if this isn't in stress, under stress, you can remove that material. And that's why it's, so it saves on metal, it saves on weight. That's why they use I-beams. Okay, suppose you drill a hole horizontally through a tree branch as shown. Where will the hole weaken the branch the least? Near the top, near the bottom, near the middle? It does not matter. Well, think of the I-beam. The I-beam was thickest at the top and at the bottom. So let's look at here at the top. Here you've got tension. You're pulling on it. You've got tension. On the bottom side, you have compression. And just like the I-beam, there's not much going on here. So in the middle is where it weakens the least. Both the top and bottom part are under stress, tension, and compression respectively. There's no stress in the middle, so making a hole there will not weaken the tree branch. Okay. And that's the end of part 2. We'll continue on next time, I think, with arches.